So let's get started. So before I get into the details, how many of you have downloaded Couchbase and have tried Nickel? Okay, Benjamin, you don't count, but half the team. How many of you know SQL? Okay, most of you. So, okay, this is the agenda for today. So Nickel for newbies. I will try to do it in 5 minutes. The best I have done is in 7 minutes, so that we are all on the same page, people. And you will see that it looks, runs, quacks like SQL. So it's very close, but except it is extended for JSON. So we'll go through the overview. Then we go through the Nickel and GSI features in 5.0. GSI stands for Global Secondary Index. I'll introduce you to that in a minute. And then Nickel and GSI features in 5.5, which was released about a month ago, something like that. Okay, so Nickel for newbies. Okay. At its core, what does a SQL engine do? Right? What does a SQL engine do? It takes sets of relations as input, and using the given statement, whether it's insert, update, select, merge, or whatever statement, it processes that set of relations and gives you back another relation as output. That's what a SQL engine does. Okay? So NoSQL said, well, SQL is too hard to implement, but we need performance, scalability, and flexibility, so we don't have SQL anymore. That's fine for some use cases. But just because you have a new database doesn't mean your business requirements change dramatically, or it becomes different. So for simple get and puts, NoSQL API was perfectly fine. But when you have to answer what shipments are due, how much did we sell yesterday or last week, you need to write a program to process all this data from your NoSQL data source and produce the report. And that's what we did for a few years in the NoSQL world. And this has issues in terms of you have to write the program, debug, maintain, verify its correctness, and so forth. When you have to write a simple program like, find the high-value customers with orders greater than 10,000, you have to loop through all the customers. You have to group them, group the orders by the customer IDs, find the, get the sales amount, do the aggregation, and then do the filtering and give the report, right? This, if you have to do it manually, it's a painful process. For each report, you have to write a new application. So the purpose of Nickel is quite simple. We want to do to the JSON model what SQL did to the relational model. Basically, we want to be a declarative language so that you can give sets of JSON as input. We process the sets of JSON using the declarative query language you have written and give you back JSON. So there is no impedance mismatch. JSON in, JSON out. So this is our mission, right? To give the developers and enterprises an expressive, powerful, and a complete language for querying, transforming, and manipulating JSON data. This is my visual representation of this, right? You have a car, you can have a very powerful car. If you can't drive it easily, it's damn difficult. So we want to give the steering wheel you had in your relational days, even in the NoSQL world, so that you can develop your queries. You can just tell us what you need, and we'll figure out how to do it. Okay? So at its core, we work on JSON. So JSON has built-in data types, numbers, strings, booleans. It has a null value, arrays, objects, and what makes JSON powerful is you can nest these objects within each other. You can have arrays of scalars, arrays of objects, objects of arrays of objects. You can nest up to any level. That's what gives you the core flexibility. To account for and introspect the missing values, right? Null is a known value. It's a known value that has got an unknown. It's a known key with an unknown value. There could be unknown keys with unknown value. Those are designated as missing. So we added a new value, missing, into the JSON construct. In terms of data manipulation language, we'll get into detail in a moment, but we support select, update, delete, insert, merge as well. But SQL has two things, right? It's got the language and the data processing rules, as well as SQL is used in all the transactional context. So in Couchbase, we provide single document atomicity. So you have to be cognizant of that when you use the update, deletes, and inserts and merge. Let's look at the simple select statement for the newbies. Select star projects everything just like your select statement. From clause specifies the buckets you are selecting from, and where clause specifies the predicates, and the order by specify the sort order. This could be a standard statement in the standard relational database as well. So this works exactly like SQL. Let's look at a little bit more complicated query. This has unnest. So okay, let's go through this. In the projection, you have 3 columns: ID, last name, first name. Those are all. The thing to remember is in JSON and nickel are case sensitive. So you have to give, if you have mixed case in your key value names, you have to use the correct mixed value, mixed case identifier in your query language as well. So those are 3 group by fields, and then you have aggregate sum of order line dot amount. The from clause is a little bit more interesting. We have orders that unnest line items. I like explain unnest in a later slide. Unnest basically flattens your array into a flat value, and then we are joining that with orders with customers, and that's ANSI. You're joining on the customer ID. That's a standard ANSI join feature. And then where clause group by having an order by. This looks and feels like SQL. It works exactly like SQL, you guys know. So I'll go through quick highlights on the statements, and then we'll get into 5.0 and 5.5 features. So in terms of the joins, we support inner join, left outer join, and limited amount of right outer join starting with 5.5. We support the correlated and non-correlated subqueries as well. Aggregation, min, max, sum, count, average, and array aggregation as well to aggregate the arrays. And this aggregation performance has improved dramatically in 5.5 if you have the right index, and index that covers the query. In terms of set operators, union, union all, intersect, intersect all, except, except all works just like the standard relational operations. Couchbase is a hash distributed data store. So if you, in your application, if you do know the document key, you can directly fetch the document within the query. We have a use keys clause which can do that, and you can use the use keys in select, update, and delete directly to refer to one or more documents, documents within the statement. And for inserts, if you're wondering why it's not there, insert having a key is a must. Every document needs to have a document key specified in Couchbase, so that's kind of implicit. So we have the inner join, left out join, right out join, as I mentioned before. By default, we use nested loop joins, and in 5.5, we also have hash joins, which you have to specify in your statement as a directive. So when you are processing large amounts of data within your query, hash joins are preferred. So I'll talk about that a little bit more when I talk about the 5.5 features. Unnest and nest are opposite of each other. Unnest flattens the surface area. That means if you have a customer with 3 hobbies, so you want to flatten the hobbies, you get 3 documents where you have customer and hobby 1, customer, hobby 2, customer, hobby 3. You'll show the example in a moment. And nest does the opposite of it. Nest takes the flattened structures and create a single document with arrays of scalar or objects within it. And nest and unnest are the operations that are at the same level as inner and left outer joins. So inner, left outer, right outer, nest and unnest can be chained in any combination. I know some of you didn't understand nest. Let's look at the nest example easily, or a simple nest example so that we are on the same page. Here, I have, look at the from clause first. From customer C, unnest c.billing as B. And if you look at the document, the input is a single document. It has a key called B billing, and this billing is an array of 2 objects. Right? Each object represents credit cards, 2 credit cards for this customer. Now, for whatever reason, I want to flatten, and instead of referring to this array of 1, array of 2, I want to flatten it so that I can do further processing. So you do the unnest operation to get this data at the same level as your customer. So I say customer C unnest billing, C.billing as B. So the output will be 2 documents, right? Because billing is an array of 2 objects. See, here I'm projecting C and B dot type and B dot card num, because when I say billing as B, each object becomes a referenceable object in object B here. So that's why you see in the result, you see the select C. C is the whole object from the customer, and then you also have individual objects. The first one is a Visa, second one is a MasterCard. So you get those things. Unnest flattens the either the scalars or the objects within the array to be the same level as the parent object. Okay, so a lot of expressions. I mean, yes, it's easy to say, yeah, we store JSON and we give you JSON back. But going back to our mission statement, if you can store the value in JSON, you should be able to access and manipulate any value within the nested structure, right? It's easy to provide a single level, 2 level structures, but because of you have flexibility, we have customers who are storing values in 3 levels, 4 levels. You should be able to access and modify them. That means each of the expressions are composable. That means you can have arrays of arrays of arrays, or arrays of objects of arrays of objects. So you have the complete flexibility, and these are all they are called expressions for a reason, right? That means expressions can be nested within one another. Anytime you have an expression, you can nest the same expression within the other next expression. So let's go through this. So ranging over collections. So when you want to filter out an array with a specified value, use the where any C in children. That here in this case, I'm trying to look for children documents who has at least 1 child with age greater than 10. So you range over this children. When you say collections, it's array. It's an array. So with age greater than 10. So sometimes you want not just any, but every value in that collection to satisfy a predicate. So in the second example, I'm going through every R in ratings should be greater than 3. Every rating should be 3. So these are all the constructs that help you address and manipulate and filter arrays and objects and so forth, right? So just for the sake of time concern, I won't go through every one of them, but you can see the whole ranging and mapping the values with filtering. Deep traverser, that means sometimes you don't know how many levels do they have. You should be able to find some value within that hierarchy. That's why we have the within. You can construct JSON objects and arrays, everything dynamically anywhere within the query. Just like is missing and is not missing, we have the just like is null and is not null in SQL, we have is missing and is not missing to introspect the JSON document. Okay, architecture. There is a simple architecture with Couchbase can be run on your laptop as well as a large cluster. Let's go deeper into it. Typically, people deploy multiple services in each service distinctly in different nodes. So you can have 3 data services, 2 query service, 1 index service, and an analytics service. And now, you saw the announcement today, we have Nickel for query and Nickel for analytics as well. There are some small differences, but in terms of the performance, in terms of the GSI indexing, what I'm going to be talking today is about Nickel for the query service as well as the index service. Right? I'm not covering the nickel for analytics, there have been separate sessions, just so that there's a distinction in it. Okay, how does nickel work, right? Finally, it's all about execution. Your application, whether through SDKs or other APIs, you issue the query, and we get the request through the REST API, and query engine does parsing, semantic analysis, as well as create a query plan. For those of you who know relational databases, that's what the query layer within standard relational databases does as well. Once the plan is created, we issue the scan request if we are choosing one or more indexes, and we push down as much as possible to the index service. Index gets us back the qualified document keys. If it's a covered index, we also get all of the data from the index service. And then if it's not a covered, if the query is not covered by the index, we go to the data service, fetch the documents, apply the filters, and do the pre-aggregation, aggregation, pagination, and projection, right? Let's see another angle of how the query processing does. These are all the different stages, right? From parsing to projection, the data flows through different stages, and not every stage is there for every query, right? It depends on the query. This is a recipe of all the operations that the query engine has. So depending on the query, depending on the plan, it could be simpler, it could be very complicated as well. We could have sub-queries, we could have multi-level queries. So this is kind of a simple recipe of all the operations here. When you see a single long bar, that means this is a serial operation. Parsing and planning is a serial operation, whereas scans, fetches, join, filter, they can all be parallel. The fetch of the documents is always in parallel. Everything else is controlled by parallelism parameter for the query. Obviously, I cannot cover everything that we have done before 5.0, but we have a thick book, so we have written a lot of details about it, and in addition to our great documentation. So read this, as well as if you really want to learn nickel, you should go to query-tutorial.couchbase.com. Nothing to download, nothing to this. You can just try out, and you can even change the queries within that panel and play around with it, so you'll learn easily. So let's see what we have done so far. Okay, so we released Couchbase about 3 years ago. We released nickel in Couchbase 3 years ago in Couchbase 4.0, and from 4.0 to 4.1, 4.111, 4.5, 4.5.1, we have been adding features. I won't bore you with all the details. And as you can see, 5.0 was a big improvement over the previous generation of our releases, and 5.5 is another improvement as well. And 6.0, you have nickel for analytics released. Okay. So I wanted to get a single sheet of comparison to SQL and nickel. Obviously, I won't go through all these things, but this slide should be available for you to just compare. And just because I say we have an optimizer and SQL optimizer, yes, we still have a long way to go, but we have done significant improvement in terms of improving our rule-based optimizer, index selection, added hash join in addition to the existing nested loop and everything. But this just gives you a comparison. We try to stand on the shoulders of giants. That's what we try to do. Okay, so with that introduction, so let's go through the features in 5.0 and see where we are. This is a summary slide of all the features. Like I said, I usually run a 5-hour workshop going through each feature by feature, discussing the performance implications, but this will be a kind of a quick run through of all the features. Like I said, this thick book has the details, gory details of all the features, but let's see what we can cover at the high end. Okay. So index key correlation. There are two things, right? When we talk about nickel, nickel has two parts. You saw the query processing engine as well as the GSI index, right? Just the query engine without the right index is not so interesting, not so useful, right? so just the index without the query is also not useful. So the query engine and the GSI, they work very closely, and the query engine does all the index selection and so forth, so we work very closely. So I'm going to cover both the indexing as well as the query features in 5.0 and then 5.5. So prior to 5.0, the index keys didn't have the ascending descending option. That means everything was sorted in the ascending order. So that means when you had to issue query where you had to sort things by descending, you had to get all the data, do the sorting, or the workaround was you had to create at least for numerical values, you could create an index with negative values, and you could rewrite the queries instead of something less than, you have to provide something greater than the negative value. It was a little bit complicated, but in 5.0, you can add an ascending and descending modifier to each of the index keys so that your queries become natural, and we optimize this ascending descending requirements to match the ascending descending correlation given in the index key. So that it saves you a lot of sorting time for your pagination queries. Large index keys. Okay, so as you develop your application, the number of the size of the keys can grow as you add more indexes. We had a limitation before that, the size of the total number of bytes of all the keys can only be up to 4096. For array keys, it used to be 1024, basically 10K. In 5.0, we have just removed that restriction. Your index key size could be up to 20 megabytes. Having said that, I don't recommend you creating the indexes with 20 megabyte key size. It's not going to be fast, it's not efficient and all that. But you design your index to be, let's say, 1K, the sum of all the keys are 1K. Some rogue data came in, and your description, for example, happened to be, we are a schema flexible. That means the data node, when you insert the data, we don't restrict that size of your description. Somebody put in a 10K description in their bio. They thought a lot highly of themselves. But if you cut off at the 4096, you lose some value. You could do substring and like and few other things that you lose the value of that. So that's why this is an exception than a norm, right? It's good to have efficient indexes, but if the data happens to be longer, you will not suffer from data loss. That's what this is, right? You are protected. If you want to partition the index into multiple indexes, you can give one of the keys and we hash on that. But each of the indexes still require the index keys, right? So when you create the composite index with a customer ID, first name, last name, you still need to give those keys, right? It works, you can think of this as a traditional relational database index, the B-tree indexes, where you have to give the leading key and all that. But when you have to partition, you can give a partition by hash of, let's say, account ID. So you create multiple indexes, you hash that. But index keys are necessary. That's the reason. Okay, index replica. So, they say one of the key tenets of NoSQL is availability. You want the and the partition tolerance, even if the one node goes down, you want the application still to be available. So previously, you could create multiple indexes with the same key definition here, C1, C2, C3, but you had to manually create it 1, 2, 3. In 5.0, you simply create a single index and say num replica to 2. It will automatically create 3 indexes, right? Num replica 2 means by default it is 0 if you don't give anything. It creates 1 index. If you say num replica 2, it creates 2 additional indexes. Okay. Okay, in terms of storage layer itself, prior to 5.0, you had the forest DB indexes as well as the memory optimized index. Memory optimized index, you had to keep everything in memory. Forest DB you could support indexes that were larger than the memory. Now with 5.0, we introduced the plasma storage engine, which was a replacement of the forest DB indexes, which is much more powerful. It's based on a new data structure called lockless or lock-free skip list, and it's much more performant and efficient than the previous forest DB index. So from the usage point of view, choose the standard secondary index in the installation, and simply create any other index. It will automatically choose the plasma index. There is no necessity to provide any storage specification in your create index. Your create indexes index statements will work as normally. Okay, now this is we are getting more into the language examples. So in the from clause, typically you say, okay, from table, from that, or from subquery. So this is a subquery and an expression as well. Here we have an array expression. In the from clause, we have an array expression for I in. There's a subquery here. That's why I say, when I say expression, it's a very generalized. Implementation. So here you can not only select from a standard bucket and so forth, you can select from any expression, right? You give an expression, and then the beauty of query processing in JSON is everything is JSON. And from the ground up, we introspect the data to find the schema. We don't need the schema additionally. So since every expression in NQL returns JSON, so we support every expression in there, and every expression returns a result set, and this result set is named as words. And then once you have this words as a result set, you can do unnesting, joins, right out join, left join, anything to your effect. So that's what in 5.0 we have introduced the concept of subquery expressions. That means in the from subquery you can give any expressions, and result of that could be joined and processed by using the select statement. Okay. If you remember the data types within JSON, it does not have a date-time data type. Date-time data type is not in JSON natively. So, but every business application requires a date-time data type. So we support the standard ISO 8901 format. You have to store it as a string, but we have provided about, I think 150 or 200 functions to do extraction, conversion, and date-time arithmetic, because you want to say, oh, I want all the data between today and 1 week before, right? That you should be able to express that easily. So we have provided extensive functions, and we have also made sure we have done the analysis between Oracle date-time functionality and us. So everything that you can do in an Oracle database, you should be able to do that with date, time, and date time with time zone. If you can't do something, let us know. We'll take care of it. Next thing, curl. Again, this is another beauty of JSON. Not only we are storing JSON within a database, every external public endpoint now talks JSON, right? So now, because we handle JSON natively within NQL, we can simply call an external microservice or internal microservice that returns JSON and do processing from there. So curl basically does exactly what the curl does as a command internally within the query engine, and we have put in enough effort to make it very, very secure, right? Because you don't want any Tom, Dick, and Harry to be calling some random microservice, but you can say which IPs are allowed, which IPs are disallowed. You have the whitelist, blacklist, all those security with HTTPS support is provided. So that's the, let me show you the example. So here I'm searching for Santa Cruz in Spain using my Google Developer API. I'm just calling the Google APIs with, I'm looking for Santa Cruz in Spain, whatever. This is the query, so I get the results from Google API. Now, that was a simple getting of the curl, but once you get, the result of this APIs are JSON. So again, you can, here I'm using a translation API to say, okay, I have some data, and I'm posting the data to the Google Translation API and getting the translation back. So we have customers doing this live translation of any text, and you can do that within the query engine. This is kind of the architecture of how this works. So just try it out. It's a pretty straightforward thing. So language infrastructure, we added a lot of bitwise functions. Sometimes you want to manipulate the bits themselves. So this is all the bitwise operations are supported in the query language as well. In terms of optimizer, so prior to 5.0, when you had to do multiple index scans within a single query block, so those could use different snapshots. Remember, indexes are maintained asynchronously with Couchbase, so they could use different snapshots. So here, even when you have multiple query ranges within a single query block, it uses the same snapshot. So that's what we call the stable scan. So you get a consistent result from the same snapshot. All the different consistency requirements that you can specify, whether it's cell equals OK, C equals false, that means unbounded or request plus, that still applies here. We have made the query faster because previously when you had multiple ranges over multiple composite keys, the index would apply them separately, and we would get a lot of false positives which we had to filter. I mean, there is one philosophy in query optimizers that has worked for the last 40 years. If you want to improve something, you have to find a way to do less work, right? So this is by pushing down the multiple predicates and also applying that efficiently in each range scans, indexer is getting us less data, or in fact, we don't get false positives. So we do less work, so your query performance is faster. Pagination is a very common use case in enterprise applications. So pagination means you use order by, when you search for something, you say order by date, and I want the offset 0, limit 50. I'm trying to get the first page. And then user changes mind, no, I don't want it by date, I want it by price. So it's a different order by, but you get the first page, limit 50, offset 0. So then for the second page, you say offset 50, limit another 50. So as you go through, every query should be efficient and fast. So what we have done is, if you have the right index to cover all the predicates as well as the order by, then we push down the limit and the offset to the index scan itself. When you see the explain, you can see what the offset and the limits are pushed down to the index scan. And then if the order by matches the index key order, that means the index is already organized by the order that you want. We skip the whole sorting itself. Okay, so okay, I'll skip over these simple things so that I can cover little bit more important things. So index, so you could have a wide index with, in this case, I have 6 keys, and in the query, I say, okay, I want the meta ID K1, K5, where K0, K1 is K0 is greater than 10, K1 is greater than 20. In this case, we don't need to ship all of the data. This is a covered query. We don't need to ship all of the data within the index to the query. So we only need indexer puts the predicate on the K0, K1, but we are only interested in document ID, K1 and K5, and in the index projection, we tell the index, project only these two keys. So again, going back to the previous principle, the less data we need to ship and manipulate, the faster your queries will be. That's what we did in FireDot. Previously, we used to get everything. Now we get only the things we wanted. Okay, that's the index projection. So let me, if you have a covered index, you can index the cache and expiration with the indexer. If you have a covered query, you can get it, make sure it's a covered query. So I'll skip over these things so that we can get to the FireDot. Okay. In 5.0, we also added something called universal index. If you don't know what kind of or if you have a document with 100 key values, and if you have a menu-driven reporting system, if you don't know what predicates are going to be generated by the reporting system, then you can't design an index for them, right? So if you want to, for a 50 key document, if you want to create the right index for every combination, it's a 50 factorial. It's a big, so you need to create those many indexes. So this may be the case of, this is more than number of atoms in the universe or something like that, right? So for that, I mean, there is an elegant answer to this. So you can create a index on individual keys, and the optimizer will use what. So you only need to create 50 indexes. Optimizer will choose individual indexes and do the intersection or apply the Boolean algebra on top of it. Again, so again, due to lack of time, I don't go too much detail into this, but this is not a silver bullet yet, right? Because when you have a query like country equals US, state equals California, zip code equals 94040, so we fetch more data, and we do some optimizations, but we still have to do more. So if you know the reporting pattern, create the composite index. When you don't know, create those individual indexes, so you can get the benefit of the intersect scan. A lot of security features have gone into 5.0. Grant revoke to the rows, just like grant revoke in the related systems. Lot of improvements in the monitoring and UI. How many of you used Visual Explain? Yeah, so Visual Explain, again, Visual Explain, if you have used in 5.0, 5.5, it has improved further, and also we have added profiling in both in 5.0 and 5.5. When you run a query, it's easy to see what are going on. So you can get the profiling by command line and get all the details, but when you do it in the workbench, it's fantastic. It shows that when you see this, let me see. When you see this query plans with all the dark yellow buttons, that means those phases are taking more time. So that's where the bottleneck is. So yeah, so we have a lot of proof points to show how 5.4 is much better than 4.5 and so forth. Let me go quickly into 5.5. Okay, 5.5. Again, this will take another 3 hours to explain all the improvements. Let me try to do it in the next 12 minutes. So we supported inner join, outer join previously, but we supported only with the on keys clause where you had to have a parent-child relationship. So I'll explain that in a moment. So we have generalized that here. A lot of performance improvements, especially with the group by and aggregation. And we added nickel auditing for security, as well as support for IPv6 and X509. And Visual Explain has been improved. Tableau document and parametric wise, everything has improved. Okay, let me talk about two features. If I cover them, I think rest of them. Okay, whatever I have not covered, thankfully we have written another book. Guide to nickel features in Couchbase 5.5, and the examples here are from mostly from travel sample. So you can just simply cut and paste the queries into your workbench. They all work, so it's very easy. And I said cut and paste. Yes, if you're not picked the books, pick up the books. and we also have it on the PDF. If you search for it, you get the PDF. You can cut and paste easily. Okay, let me explain these two features. ANSI join. These joins are specified in the SQL standard. It's supported by all the relational database systems that you guys know about. And prior to 5.5, we supported the left-outer join and the inner join only with the parent-to-child relationship, and you had to have an equality. That means you had to have a parent store the key of the child, or child document store the key of the document. Simple example is every order document has a key of the customer document ID. You have to have that, then you have an equality predicate. But real world is more complex. You want generalized index. So the equivalent of that is, you can have customer inner join orders on customer.id equals o.customer ID. It's a pretty standard ANSI join syntax. This is the new update. Previously, you had to give on keys and all that. So just stick to this standard ANSI join. You'll be fine. We still support the old version for those of you who use the old version, but this is the new word. We support inner join as well as the left outer join, as well as the right outer join. We only give support the right outer join in the first as the first join. We are working to improve the rest of it. And now, so far you saw simple equality predicate. You can put on the on clause, you can put any kind of expression. You can put a complex expression. In this case, I have in the on clause b.brewery_id equals, there's a string expression with on the right hand side, and b.type equals beer. You can have and or whatever, anything that you can put, any expression you can put in there, you can put in here. The requirement for that is you should have index on at least one of the keys of the index, so that we don't end up doing a primary scan on the whole bucket, right? So we want to avoid that. Yeah. So the syntax is you've seen sample syntaxes: inner join, left outer join, and right outer join. Let me see what's more important. Yeah. ANSI joins uses indexes on both sides of join. That's why it also called the index join. We first apply the where predicate. After that, you do the join predicate. So these are all the standard things you know. Yeah. I have an example on the hash join. So let me just see. Okay. Before I show the hash join, so one of the things about implementing this standard SQL features is not only we implement just this language, but also we have to extend it for JSON. So JSON has arrays and objects. So this ANSI join and inner join and left outer join supports both arrays and objects. So you can give, I'll show you the examples. Okay, let's say you have example product and purchase. You can give, say, okay, in this case, I have a query with the product join. By default, it's inner join product, inner join purchase. Remember we had the expression on ranging over collections. So that's the any expression. So here, in the on clause, we have an expression that joins P with PU. So any L in the PU.line item satisfies L.product_id equals P.product_id. That means we have not only implemented left outer join for simple scalar values, we've extended for arrays and arrays of objects as well. You can give any kind of expression that we saw previously here. So that's the power of ANSI join. Let me skip over these things. We support ANSI. Okay. By default, we use the what we call the block nested loop join. In 5.5, we also implemented the hash join. When you are processing a lot of joins, for example, the analytics service that you saw the demo earlier, it uses hash join exclusive almost every time because it is processing a lot of data for analytical queries. For us, we are running a lot of queries, but each query is processing less amount of data, so we favor the nested loop by default. But if you say use hash join and give which side is the probe side, which is the build side, we use the hash join. When you start processing tens of thousands of documents in each query, we recommend you use the hash join because the performance of that tends to be 3, 5, 10 times. As the amount of data that you process in a join increases, your performance is going to be that much better with the hash join. Okay, so I'll cover one more topic, then I close down. So sorry, I've taken most of the time, and I'll be around and in the connects bar if you have any questions. Grouping and aggregation, right? In query processing, joins, grouping, and aggregations are the most expensive part of the processing. So in Couchbase 5.5, if you have a index that covers the whole query, right? That means the query becomes a candidate for what we call as a group by acceleration. That means the index engine, previous to 5.5, index simply did the scanning. We give the range or a point lookup, it did the point lookup or the range and returned. In 5.5, if the index covers the query and it has to meet few additional requirements, then index not only does the range scan, but it also does the group by and aggregation. So your performance is typically 10 to 20 times faster. In this case, I have an index on type, and if you see here, the query is select type. I'm just trying to see how many types we have and counts for each type. I have a select type, count of 1 as type count from travel sample where type is not null, and group by type. The where clause type is not null has to be given just so that we choose that particular index. And now this gives me back the results in a few milliseconds instead of seconds here, right? So these are the types of the sample aggregation queries. So you saw the first query before. Well, here I'm just selecting the type without the count. You can have any combination of group by and aggregate. I'll show you a little bit more complex query here. Here I have multiple group by columns, and I have all these aggregates, and then I am doing a group by on this. So even this query, given the right index, will get accelerated. So let me show the last two slides. So typically, what you saw this slide earlier. Typically, we use the index service to do the filtering on the range scan or the point lookup, and then the query service does the pre-aggregation, aggregation, and sort. If you have a covered query, we avoid going to the data service, but the query service still has to do the filtering, aggregation, and sort. With 5.0, if you have the right index designed for the grouping and aggregation, we scan. Index does not only the range scan, it does the grouping and aggregation, so that, what do we save? We still have to do the calculation, but we avoid shipping, right? If you go to the art of programming, one of the best ways to optimize your program is to avoid copying. Data copies and loops are the biggest issues. So this avoids all the data copying, and you get the best performance. So here's a example of a query. So this query here, we did a lot of performance benchmark. This query here in 5.0 took 21 seconds with 2 queries per second in our setup. This is a complex query handling a lot of data. In the same query in same setup, 5.5 with the right index ran in 0.7 seconds and had 80 queries per second. That means 30x improvement in the latency, 40x improvement in the throughput. So I'll stop there. So again, so ton of improvements in 5.0 and 5.5. So I'm trying to get to this slide. If I didn't cover something, it's here. Thank you very much.
Keshav, thank you very much. All kinds of, and I did misread the abstract, by the way, so sorry about that. If you have any other questions for Keshav, he's going to be out here. I also have some nickel experience. You can ask me if you think of something after the show. You can also reach out to us on community.couchbase.com or the forums.couchbase.com. Thank you very much.